This is a video from the topic B2, organisation, and focusing today on the human digestive system. So first of all, let's look at what digestion is. Digestion is where enzymes take large insoluble molecules. Insoluble means that they cannot dissolve in a liquid, and turns them into small soluble molecules, and they need to be soluble, able to be dissolved, so they can be absorbed through the wall of the small intestine through the villi. An example of one of those large insoluble molecules is starch, and starch breaks down into the small soluble molecule that is glucose. Glucose is then soluble, so it can be dissolved in a liquid, and then it can be absorbed through that wall of the small intestine. Let's have a look at the organs of the digestive system. Not going to talk about them a lot here, just going to identify where they are in a picture. This gives us those quick one-mark questions where you've got a picture of the digestive system and the question says put an X on the liver or put an X on the stomach, or they're lettered and it's which letter represents the small intestines, for example. So the organs in red, food doesn't enter those organs, and the organs in black, food passes directly through those organs. So 1 is the salivary glands producing saliva, 2 is the mouth, 3 is the esophagus taking the food from the mouth to the stomach, 4 is the liver which produces the bile, 5 is the stomach, 6 is the gallbladder which stores the bile, 7 is the pancreas which makes lots of the enzymes. 8 is the large intestine, 9 is the small intestine. Now food actually goes in the small intestine before the large intestine, and then 10 is the rectum. So let's start at the very beginning. We'll start with the mouth. 2 types of digestion occur here in the mouth. We've got mechanical digestion, which is the teeth chomping away at the food, which all it does really is it allows us to swallow it, and it increases the surface area. And increasing the surface area is going to help the food later down the line when the enzymes are digesting it properly, chemically. There's also some chemical digestion in the mouth, and this is in the form of amylase. Amylase is an example of a carbohydrate enzyme, more of that in the enzymes video. It's made by the salivary gland, and it digests starch into glucose in the mouth. Now, food doesn't really stay in our mouth very long, so we don't really notice that this is happening. But they do say that if you take a piece of bread and you keep chewing on it for a good 5 minutes, it does start to taste sweet because it's had enough time for the amylase to break that starch into glucose, and then you can taste the sweetness of the sugar. We can see from the picture, we've got the amylase enzyme with the active site where the starch is sitting in there. The starch is that long, large insoluble molecule. You can see it's a chain of molecules, and then it's been broken down into glucose. So in the mouth, mechanical digestion of the teeth, chemical digestion of amylase, by amylase of starch into glucose. Let's have a look at this. Okay. Next, we go to the esophagus. Now, the reason that we eat fibre is because it helps to bulk up our food so that it can move through the digestive system. And on this picture in the top right there, we can see that we've got kind of this lump of food. We call it a bolus. Don't worry too much about that word. And the muscles just above it contract, which pushes that food through the esophagus. This method is also used in the small intestine and again in the large intestine. And the fibre bulks up that food so that it's easy to push it through the system. Okay, so it doesn't just kind of get lodged and stuck in the area. And that process of moving that food through the esophagus is called peristalsis, okay, where the muscles contract above the food and push it through the esophagus. And it's fibre that helps that to happen. Okay, fibre isn't digested, we don't break it down, we don't absorb it into the bloodstream. The only purpose of fibre is to help the food move through the esophagus and the small intestine, the large intestine. Next, we're going to the stomach. We've got part 1 here because there's a lot happening in the stomach. In the stomach, we have hydrochloric acid. Try not to be tempted to call it stomach acid. Try to call it hydrochloric acid. It's around pH 2. This has two jobs, two functions. One, kills bacteria. Obviously, if you've got something like food poisoning by salmonella or something like that, the hydrochloric acid isn't able to get rid of all the bacteria. That's why you might get sickness and diarrhea and not be very well. But primarily, the hydrochloric acid kills bacteria. And then we've got some enzymes working in the stomach, okay? Things like the protease enzyme pepsin is working in the stomach. And the pepsin works really well. Its optimum conditions are acidic conditions. So the acidic conditions enable the enzyme pepsin to work in those optimum conditions. Okay, so they need to have the right pH. We know that they need to have the right temperature as well, but pH is really critical to allow these enzymes to work. The stomach itself needs to be protected by from the hydrochloric acid, and there is a mucous stomach lining. Okay, so this mucous lining enables the acid to not be able to attack that stomach. Okay, and if you have a gap in that stomach lining, then you can get a stomach ulcer where the acid has just started attacking the stomach lining. We also have mechanical digestion in the stomach. This is because the stomach is a giant muscle, and the word that they like you to use is churn. So the muscles contract, because remember, muscles can only contract or relax. So they contract and relax to churn the food, to help kind of mix it all together, give it a little shake around, okay? Mechanical digestion was the churning. Chemical digestion, we've got those enzymes, which remember we said we've got the large insoluble molecules becoming small soluble molecules. And one of the examples of the enzymes in the stomach is the protease enzyme pepsin. Okay, let's move on. So here are some pictures of the stomach, just for interest's sake. And now we're moving on to the small intestine. Again, lots and lots happening here in the small intestine. So this is where the liver and the gallbladder have come into play. The liver made the bile, and the bile is slightly alkali. And when the liver makes the bile, it then concentrates it, or you could just say stores it, in the gallbladder, which is just a tiny organ just below the liver. This has the effect, again, two functions. The first one is to create the right conditions for enzymes in the small intestine to work. Here we've got enzymes like the protease enzyme trypsin. So you may have seen the graph of pepsin and trypsin. Pepsin works well in the stomach in pH 2 or 3, and trypsin works really well in the small intestine where the pH is around about 8 or 9. Okay, so again, it's creating the optimum conditions for the enzymes that work in the small intestine. Now, the small intestine equally doesn't have that protective mucus that the stomach has. Okay, so it would be bad for the small intestine if the acid were to come into it too much, because it would basically destroy parts of the small intestine. So creating a slightly more alkali condition, neutralizing that stomach acid, enables the enzymes there to work better. And we've got other enzymes working in the small intestine as well. We've got lipase, and we've got more of the carbohydrates. The other really important thing that the bile does is it emulsifies fat. Now, it's really, really good to remember the word emulsifies, but then you've also got to be able to explain it to show that you know what emulsify means. And it means to increase the surface area of fats, okay? Emulsifying is not a digestion process. It's almost like if you imagine you've got a block of butter and you cut this butter with a knife. If you just put it all back together, it would stick back together. But what the bile does is it coats the fat. So it would be like coating the butter in a layer of sand, okay? That's the effect that the bile has. Bile is not sand, but it has the effect of breaking down, almost like using a knife, the fats, coating them in this layer of bile so that they don't stick together again, and therefore increasing the surface area. This means that when the lipase, the actual enzyme that breaks down fat, digests fat, comes into play, it's got a much larger surface area. It's much more efficient at breaking down that fat. Let's move on. So small intestine part 2, so we're still in the small intestine. All molecules that can be digested are now digested, okay? They're all soluble, small, and ready to be absorbed through the walls of the small intestine by the process diffusion, okay? I think we've talked before in B1 about the villi in the small intestine. They increase the surface area of the small intestine. There's even microvilli, which increase the surface area even more. And this word absorb, think of it like a sponge. It's the small soluble molecules moving from the small intestine into the blood. Okay, first of all by diffusion, and then I talked in a B1 video, the diffusion and examples of diffusion, about the fact that first of all there is a concentration gradient. There's more glucose in the small intestine than there is in the blood. So the first part of that movement from the small intestine to the blood is by diffusion. And then when the concentration of glucose is the same in both the small intestine and the blood, the last part of the glucose is moved across by active transport, which is that movement from low concentration to high concentration. So small intestine, we've got all of these digested molecules now moving into the blood. Anything that's undigested will move again by that process peristalsis, where the muscles contract to push the food through to the large intestine. Now, we haven't talked about vitamins and minerals, and this is because they are already small and soluble when you eat them. So they don't need any enzymes to digest them. They just move through the digestive system and can be absorbed into the blood without any kind of digestion. Okay, here's some pictures of the villi in the small intestine. We said they have a large surface area. They have a very thin size so that it's easy for molecules to get through. There's a lot of moisture there so that the molecules are soluble. They must move across when they've been dissolved in a liquid. And there's a large network of blood capillaries, so lots of different places for them to go to once they get through the villi. Okay, let's talk about bile and the liver just a bit more, just to make sure we understand this process of emulsifying. So here we've got the biles made in the liver. You can see that labelled on the picture. It's stored or concentrated in the gallbladder. It neutralises the hydrochloric acid from the stomach, producing the right conditions for enzymes in the small intestine to work. It also emulsifies, which is not the same as digesting. It's just breaking down those large fat globules, that is a word they like you to use, into smaller fat droplets, okay? Coating them in this layer of bile so that they have a large surface area, they don't stick together again, which helps lipase out later on to attack and digest those fat droplets. Okay, last slide then. We're in the large intestine now. Not a lot happening here. Any water that is remaining is absorbed into the bloodstream, and then waste is removed to the rectum. Okay, so that's the end of our journey through the digestive system. Hope you found that useful. Thank you.